In mathematical induction, we want to use a proof to prove that this sequence is true for all positive integer values of n. Now, the way that the mathematical induction works is first, if p of 1 is true, that means if I plug in 1 for n, then I should find out that 1 times 1 plus 1 over 6 is the same as the first term in the sequence, which it is. 1/3 is the first term. So then p of 2 should give me the sum of the first 2 terms in the sequence, and p of 3 should give me the sum of the first 3 terms in the sequence. But how do I know that this holds true for all values of n? I don't. So we use a process called mathematical induction. What's going to happen is I'm going to assume this is true for n equals k. So that means if I replace n with k, this is going to be true. If this is true, then I need to prove that it's also true for the next term in the sequence, which is k plus 1. So I take the k plus 3, and I'm going to add it to the next term, which is k plus 1 over 3. And I want to prove that this equals k plus 1 times k plus 1 plus 1 all over 6. Where did the k plus 1s come from? I replaced any k with a k plus 1. Now we found out that this works out a little bit nicer if I simplify the right-hand side and find out what that should equal first. Then I'll go back to the left-hand side and determine if that equals the right-hand side. So I'm going to get k plus 1 times k plus 2 all over 6. And if I multiply that out, I should get k squared plus 3k plus 2 over 6. So I want the right-hand side and the left-hand side to equal each other. This is the right-hand side I just dealt with. We want to now work with the left-hand side and see if we can get it to equal k squared plus 3k plus 2 all over 6. So now I'm going to go back. And now I'm going to deal with this. First, you take the first term and you replace it with this, because we found out that k plus 3 or k over 3 is equal to k times k plus 1 over 6. So k plus 1 over 6, over 6. And I'm going to add to that, go back a page, the k plus 1 over 3. And if this works, when I'm done simplifying it, it's going to equal the other side of the equation. So first I'm going to do some distributing. K squared plus k over 6 plus k plus 1 over 3 equals. I need a common denominator in order to add those fractions. And instead of doing it the way I did it in class, I want you to notice that I can make the second fraction have a denominator of 6 by multiplying everything by 2. So I'm going to get 2k plus 2 all over 6. Now I can combine the numerators, and when I do that I combine my like terms and I get k squared plus 3k plus 2 all over 6. And guess what? That equals the other side. So cha-ching, I just showed with mathematical induction that this is true for all values of n. I'll do this one more time. How about I prove that 2 plus 4 plus 6 plus ... plus 2n is equal to n plus 1. So the first thing that I'm going to do is I'm going to say 2k is equal to k plus 1. That is true. In order to show that that is true, I must take the 2k and add that to the next term. And when I'm done, it better equal what I get when I replace all the n's with k plus 1's on the other side. So I want this side, the right-hand side, to equal k squared plus 3k plus 2 when I'm done. Now in order to do that, the first thing I'm going to do is take the first term and replace it with this. So the first term becomes k plus 1. And I'm going to add that to my 2k plus 1. Now I'm going to distribute and simplify. So k squared plus k plus 2k plus 1 is indeed k squared plus 3k plus 1. And that is my proof.